Most urban drainage networks in our cities are combined networks. This means that they collect wastewater and stormwater together. This mixed water is sent to wastewater treatment plants, where it is treated before being released into the receiving environment, typically seas or rivers. During dry weather and moderate rainfall, the system overall performs well. However, during periods of heavy rain, the capacities of urban drainage networks and wastewater treatment plants can easily become overloaded, causing flooding and untreated water to discharge into the environment, known as combined sewer overflows. Some cities have built retention tanks in order to avoid flooding and minimize the amount of water discharged into the environment during wet weather. When there is no risk of flooding and the treatment plant is able to function normally, the tanks are not used. However, they start storing untreated water when a risk of flooding is detected or the treatment plant capacity is likely to be surpassed. The aim is to wait until the rain intensity reduces or even stops, to empty the tank and send the water to the treatment plant. This is the most common operation strategy applied to the sewer network, the so-called local rule-based control. Certain problems may occur using this kind of strategy. If the tank becomes full before the emptying can start, it cannot keep storing additional water and consequently flooding and overflows could occur. In general, sewer networks and wastewater treatment plants are planned and operated as independent systems and coordination strategies are not considered. Additionally, sewer network operation only takes into account hydraulic criteria without considering pollution concentration of wastewater effluents. To tackle these inefficiencies, Life Drain, an EU-funded project led by Setaqua in collaboration with Aquatech, Lilia, Aquambiente and CSIC, aimed to demonstrate an integrated real-time control strategy of urban drainage networks and wastewater treatment plants to minimize the pollution sent to the receiving waters during rain events. Unlike current systems, the Life Drain strategy uses rain forecasts and real-time water quality data. Using this approach, the methodologies developed can choose the optimal strategy to operate the network and treatment plant elements such as tanks, valves, pumps and bypasses at any given time during the rain event. The Life Drain strategies always aim to avoid flooding and reduce the level of pollution released into the environment. For example, there are times that the treatment plant may not have enough capacity to treat all the wastewater. However, although there is space inside the retention tank, a decision not to store it might be taken in order to have free volume to store more polluted water that has been predicted to come in the following time instance. The system then forces a sewer overflow of cleaner water to prevent the more polluted water from overflowing. Once the rain has decreased its intensity or stopped, the most polluted water can go to the treatment plant. Obviously, it is not the same having a simple network as a more complex one with several tanks and elements of control. To prove its wide applicability, Life Drain validated the methodologies developed using a virtual reality environment inspired in two real pilot sites. Badalona, on the Spanish Mediterranean coast, is an example of a simple system with a certain degree of control to minimize flooding and pollution sent to the environment. Badalona pilot covers just 2 basins with 1 retention tank that can receive water from each basin. In France, the selected pilot site was Bordeaux, Louis-Fargue catchment on the Atlantic side. Due to the high impacts of flooding and overflows, in this case, there are about 17 tanks and a high number of control and instrumentation elements. For both pilot sites, the Life Drain project proved that the proposed strategy improves the quality of the receiving waters by reducing the pollutant mass released to the environment. In particular, in the Badalona pilot, a 6% reduction of released mass has been achieved, while at the Bordeaux site, it has improved by 30%. However, the aim of the project was not only to prove that a better strategy exists, but also to promote replicating and transferring the system to other places with real implementation. Guidelines for the replicability, transferability and improvement of future European Union environmental regulation were also drafted up.